Good morning and welcome all. My name is Dylan Tanzi, Executive Director of the SunSpec Alliance. Thank you for joining us for today's webinar on 23.5 Enhanced Tools for DER Integration and Testing with the InterSTORE project. The topic for today's webinar sits right at the intersection of a lot of the work happening within the SunSpec community, particularly around interoperability, testing, and standards-based communications for distributed energy resources. As DER deployment continues to scale, making sure different systems can communicate reliably using common standards has become increasingly important. This webinar will take a look at the InterSTORE project and the work being done around enhanced 2030.5 tools for DER integration and testing. The goal is to make it easier for legacy systems and newer grid platforms to communicate with the grid while also improving how DER devices are tested and validated. We've got a great group of speakers who are directly involved with this work, and they'll walk through the tools, the architecture, and the real-world implementation behind the project. And so, just a couple housekeeping items before I pass it on. If we go to the next slide. So all SunSpec meetings are conducted in accordance with the SunSpec antitrust policy and intellectual property provisions defined in the SunSpec member agreement. This agreement can be found at the following address. SunSpec strictly prohibits market participants and their employees who take part in these activities from using their participation as a forum for engaging in practices or communications that violate antitrust laws. Confidential or proprietary information should not be discussed in open session. Please contact SunSpec management if you have any questions. And some last items, a couple notes. This meeting is being recorded, so we'll be posting it on the website and distributing it to all attendees after the conclusion of the meeting. This meeting is being held on Google Meet, so you do have the ability to unmute yourself and turn your camera on. However, for the sake of recording and for background noise, we do ask you to keep yourself on mute and with your camera off. With time permitting, we'll have some time for Q&A at the end, but I do encourage you during the webinar, if you have any comments or questions, to please put them in the chat and we can look through those time permitting at the end. So with that, I'm going to go ahead and pass it off to the InterSTORE team. Thank you all for your time and attention.
So thank you very much for the introduction. Good morning, good afternoon, actually, from my side, given we are in Europe. Everybody, my name is Antonello Monti, and I'm from the professor at the RWTH Aachen University in Germany, and I've been acting as a coordinator of the InterSTORE project. And I will be the first presenter giving you a little bit of review on the goal and scope of the project. Then we will move to talk about the legacy protocol converted and client server library that have been developed, and this will be presented by Matthias. Then we will talk about the testing procedures, and with also a short demo, and this will be presented by Nitin and Alessandra. Then we will talk about the architecture, environmental tested, lessons learned, and the main KPI reached by the project, and this will be presented by Daniele. And finally, some practical example of application of our libraries and implementation in a commercial EMS that will be presented by Nikolai. So moving forward, I will give you the key fact about the project, so the little bit of background on the structure of the consortium and so on, and on the main results, and then we'll pass to the more technical from my colleagues. So the project has been funded by the European Commission. InterSTORE is an acronym that stands for Interoperable Open Source Tools to enable hybridization, utilization, and monetization of storage flexibility. We have been funded by the European Commission, and we have been running a project for about 3 years, a little bit more than that. And the coordination was with my university in RWTH, but the technical coordination was managed by Alexander Lucas, by INESTEC. In the consortium, we had a variety of research groups together with the university and INESTEC. We also have Jülich, Forschung Center Jülich. We also had industry involved, like Eaton, or commercial aggregator like Cybergrid or Enelix, that are also here in the meeting today. And we also look at the aspect of standardization and the regulation. That's why we had, for example, a partner like the German Association VDE, that is the responsible for standardization in Germany. Getting to the project, the main goal has been to develop a middleware that allow the interoperability and data exchange. The bottom line of the idea is, as mentioned also in the very brief introduction, we have several and a variety of different DER that are being displaced, and the key challenge is to make them sure they are interoperable and they can participate in larger pictures in terms of flexibility aggregation. So they have to be able to talk to a flexibility aggregation platform or in general to a distributed energy management system. For that purpose, we identified the 2030.5, IEEE 2030.5 as a reference protocol to be used. And we decided to do two extensions. The first one to enable this over NATs, and that was a way to enable the possibility of multi-multi communication. So that's an empowering respect to the standard implementation. We're already available for 2030.5. And as we learned very well from the different demo that we implemented, and you will hear more about it later, there are, of course, components and ER that are not the 2030.5 ready. But through the legacy protocol converter, which is one of the tools we'll present later, we were able to integrate them in the overarching picture, so allowing a vision of interoperability that goes beyond a single protocol and builds a very open architecture and solution. So if we summarize the results of the project, first of all, as mentioned, it is fully interoperable solution built around the IEEE 2030.5, and this is built on three key ingredients: the real client and server based on messaging over NATs. That is the core of the solution. The second tool is what we call the legacy system protocol converter, which allowed us to bring into the interoperability system other solutions. You see here in the picture as example, that you may have some Modbus ready device or MQTT ready devices, and through the LPC, they become part of the ecosystem that we develop. And last but not least, automatic testing procedures. You will hear later about all those three tools that make the full tool set of IEEE 2030.5 that we develop. We did also further development, which has been to embedding this type of solution within the concept of data space. In Europe right now is a major effort to build what we call a common European energy data space. So a mechanism of data sharing with the possibility of adding on top of the simple communication mechanism of data sovereignty. So basically giving the user or better, the owner of the data, the possibility to control the access to the data to create profile depending on the use case that is under consideration. And what we did, we were able to map then our solution to a so-called data space connector. We started from a data space connector was developed in a previous European project called OneNet, and we did some enhancement with respect to the original connector. First of all, adding a full open source graphic user interface. So right now, this data space connector is the only data space connector that is fully available as open source for the energy use cases. We added the possibility of blockchain notarization and verification. We added the capability of push mechanism and external service integration. And of course, currently with our picture, we were able to integrate the 2030.5 as a possible data protocol. And that allows us to improve the performance respect to previous version of this protocol. Everything we developed has been seriously tested in real life scenarios. I collected here the scenarios in 4 pictures. They're all real life demo, but with different characteristics. We had a demo running in Italy that you see on the top left in the premises of NLX in their laboratory, where they are testing particularly in direction of e-mobility and charging systems. We had a demo in Germany related to the Forschungs campus in Jülich, that is a campus evolving towards zero impact. And so They're developing an internal EMS to coordinate properly the different building and different assets in the campus to achieve the final goal. We had a demo in Austria related to a local energy community, and we had an industrial demo in Portugal. You will hear more details later about the different demos. What I want to bring here as a point is those were real data with real customers and real equipment in real life, and with a mix of legacy devices and also native devices, so that we had the chance to try all the different aspects of our tool set that we develop within the project. What is also important, and that's the reason also to have a webinar, is to make everybody aware that we really believe in what we develop so much that we want to be sure that survives the funding cycle. So typical issue of those funding projects is when the funding ends, the project ends. But because we believe this type of interoperability has a commercial value, and some of our partners are, as you will hear also later, commercial, so they do it for a real business purpose, they need this to survive the project. Solution for that has been to bring the complete package of our product to LF Energy, build the project in the Linux Foundation Energy. We had to give a name to the whole package. This is called Cupid. Cupid is now an open source community that is part of the Linux Foundation Energy. You can join the community. You can access our repository, which means you can use freely what we develop, but you can also join the community, contribute to the further development, and shape the future of Cupid if you're interested to this specific set of tools that we developed. The community is running, is open, and it will be managed within the rules of the Linux Foundation. With that, I complete my part, and I will now give the floor to Matthias to talk about the toolkit and legacy system protocol converter.
Thank you very much. Thank you very much, Professor Monti. What I would like to talk about is the interoperability toolkit. And if we go to the next slide, please. As already mentioned, the interoperability toolkit consists of 4 different software solutions: the legacy protocol converter, the interoperable client server libraries, the testing procedures, and the data spaces framework. First, I would like to focus on the legacy protocol converter. Why would you use the legacy protocol converter? You would use the legacy protocol converter if you have a device which communicates in an older protocol, such as Modbus, MQTT, or similar, and would like to integrate it with some other devices using the IEEE 2030.5. The legacy system protocol converter is basically a microservice. It runs on a variety of devices, such as regular servers, virtual machines, Docker containers. It can also be run on smaller devices, such as Raspberry Pi or any other gateways that are used with the devices, and we have also tried this out. It has a modular architecture, so the software architecture is really modular. Currently, Modbus and MQTT are supported on one side, and of course, NUTS is supported on the other side. But the modular software architecture allows it that other protocols can also be implemented, and we have already implemented support, for example, for RabbitMQ communication, and other protocols can also be added. As already mentioned, this is open sourced under the MIT license, so everybody can use it, extend it, and even contribute to the project. Now, the most important part here is we haven't just used the IEEE 2030.5 protocol. in its regular format. We have supported everything in the specification, of course, but we have also extended it. So in addition to the XML representation of the messages, we also support the JSON representation and for all the 321 elements that exist in the standard in the specification schema. Also, we have implemented the NUTS communication. So the regular IEEE 2030.5 is based on the REST API. And REST APIs are very common today, very widely used. However, NUTS communication, which is cloud native messaging, is a really high performance messaging system, which provides several benefits. On one hand, it is asynchronous communication and allows new messaging patterns. For example, not only one-to-one. What does this mean? That only one device communicates with one EMS system or something like that. The NUTS messaging, which we have supported, provides support for one-to-many and also many-to-many communications, which means that a single device can communicate with multiple other systems, EMS systems and other devices. And this figure that you can see here demonstrates this. We can see in the upper left-hand corner, we can see a Modbus device, which uses the legacy protocol converter, which converts the Modbus messages to IEEE 2030.5 and puts them into the NUTS messaging cloud. On the bottom left side, we can see a device using MQTT in the same way. And on the right side, we can see an AMS or a similar system. One uses the MQTT, and we can also see some IEEE 2030.5 native devices and systems. So this is the common interoperability picture. And now if we move forward, there are some key features of the legacy protocol converter. One of them is the built-in transformation framework. So it is relatively easy to specify how the transformation from Modbus or MQTT or other supported protocols should be done to the IEEE 2030.5. It is basically a transformation file which specifies all the incoming parameters and how they are mapped to IEEE 2030.5 schemas and vice versa. It is also worth mentioning that the LPC supports multiple transformations. For example, on the previous figure, we have seen 3 different LPC boxes, but it is not necessary to run an instance of an LPC for each and every transformation, because a legacy protocol converter can handle multiple transformations, incoming and outgoing transformations. And as I've already mentioned, we can deploy it on really huge variety of devices, everything from small embedded systems such as Raspberry Pi, IoT devices, and so on, all the way to the virtual machine servers. It is also Kubernetes ready. It can scale. There are security mechanisms built on, and so on. If we please continue to the next slide. As I've already mentioned, the NUTS messaging is the backbone. I have already explained the one-to-one, one-to-many, and many-to-many communication patterns, which we believe is quite important because it can simplify integrations, it can make them more reliable, and it also opens up some new opportunities how to connect and integrate devices and EMS systems. Next slide, please. If I go a little bit into the details, so the legacy protocol converter has been implemented in Java, and it can basically run anywhere where you have a Java runtime environment, which is more or less every system today. There are all the main operating systems are supported, and as I've already mentioned, the requirements for running it are quite low. For example, 256 megabytes of memory and any reasonable processor are adequate. You have several options how to run the legacy protocol converter. The most straightforward one is to use the pre-built Docker image. On the Docker Hub, we have published pre-built legacy protocol converter images and very simple instructions how to download those images and run them. There are other possibilities. Of course, you can run it as a Java archive, a jar file, or you can even build it from the source code, which, as mentioned, is available on the GitHub. Next slide, please. Just to get an idea how the legacy system protocol converter is configured, this figure shows in the upper left corner a simple MQTT message in JSON. On the right side, you can see IEEE 2030.5 in XML, and down below is the transformation file. So the transformation file is a YAML configuration file where you specify different parameters, everything from the connections, incoming, outgoing connections, and to the actual mapping. I don't want to go into many details, but if we just go through the next few slides, you will see the idea. So this slide shows the connections that you specify. Here we can see that we have a NOT server, MQTT broker, and a Modbus battery. You specify different parameters for different types of connections. Then on the next slide, we can see the transformations. We can specify multiple transformations, and all can be handled by a single legacy protocol converter. If we go on, please, to the next slide. Here it might seem a little bit complex at the first sight, but once you understand the structure, it is relatively easy to master. If we continue, please. Here is again the first was the incoming. This is the outgoing transformation. Next slide, please. And we have also built in some additional features such as interval requests, where a legacy protocol converter can request or send a message in a specific time intervals or at a specific triggers and so on. To simplify the configuration, we have also developed a user interface. This user interface is available on the above link shown on this slide. And it's basically a web application which simplifies and guides you through different screens, menus, and options. And once you are done, you can download the configuration file, which you then use with the legacy protocol converter. This is again a screenshot from that user interface. And if we continue to the next slide, please. So the latest version is from October 2025. There are a lot of different features that I will not go into the detail today, but if somebody is interested, everything is also documented on the GitHub, on the README file, and on the release notes. On the next slide, we can see the other important development that I would like just briefly to mention. So on one hand, we have this legacy protocol converter standalone microservice, which can transform the messages from older devices. But we have also developed the client and the server libraries. These are software libraries that can be quite easily integrated into the firmware of the devices or into the EMS systems. And they enable the IEEE 2030.5 compliant communication over NATs with XML and the JSON support. So, for example, if a device producer, for example, a battery producer or something similar, or an EMS software vendor would like to integrate this type of communication, they can use those libraries and integrate it into their software. We have done this in the InterSTORE project. For example, Cybergrid company has successfully integrated this with the CyberNOC, and we will hear about that a little later. This figure shows all the libraries and the different and the different options how those library can be used through direct integration, through Modbus, MQTT, and all the other possibilities. If we continue, please, here are the links to the GitHub repositories of the Qpid project, which Professor Monti already mentioned. And there you can find all the repositories, the legacy protocol converter, the client and the server libraries, and the testing procedures, which we will hear about a little later. On the next slide, we can see the link to the Docker Hub. In the Docker Hub, you can download the legacy protocol converter pre-built image. We currently have already 1,500, more than 1,500 downloads, and it's increasing from week to week. Yeah, and basically that's it from my side, and I will give the floor to Nitin to talk about the testing procedures. Thank you very much.
Hi, thank you, Matthias. So here I want to talk about the open source IEEE 2030.5 testing software based on SunSpec testing procedure. Next slide, please. So this is the architecture. In this architecture, you can see 4 parts. The central part is the IEEE 2030.5 server itself. The IEEE 2030.5 server is where all the resources of 2030.5 is got stored. It's based on REST API as per the 2030.5 standards. And there is a front end. And the front end is the place where the user can go and interact. User can create the test cases. So user has to put the input of the device under test. So there is another layer called client layer. The client layer actually sits on premise where the device is located. The rest of the 2030.5, the server and the front end that can host it in a cloud. In a demo, we actually hosted this is in Amazon Web Service in Arizona, and the client is in Italy, in Rome. So the client layer has a thing called ad hoc server. This ad hoc proxy server is directly connecting to the client DER, which is a Schneider device. Then there is another block called the messaging layer. This is where once the test is completed, this will publish via NATs to whoever want to subscribe it. Next slide, please. So this is the Italian pilot. I was talking about the XU, this NLX laboratory in Rome. They have 2 batteries. One is Pilentech and one is GreenTech. And these 2 batteries are connected to the Schneider IEEE 2030.5 gateway. And this architecture can be 2-way, like the ad hoc server, the proxy server that gonna connect to the testing software can be hosted in Raspberry Pi or in a normal computer, like in Linux or in Windows. Then this ad hoc server comes with the certification. The certification is called the CS certificate to do the mutual TLS handshake. This certificate has to get from SunSpec, otherwise it doesn't work. So thanks to SunSpec for providing this certificate to connect to the device, to this proxy server. Then from the proxy server, it's going to connect to the cloud where the testing software is hosted. Next slide, please. Can you move the slide? Okay, thank you. So this is the complete architecture of the Italian pilot. As you can see that there is 2 paths. One is from Modbus and one is from 2030.5. So these 2 things are both connected through LPC. The LPC is the one shown by Matthias in the preceding slides. So through the LPC, it's connected to the data space connector, and it is going to the upper control platforms. Next slide, please. So this is the complete infrastructure in the Italian laboratory in NLX. As you can see that they have V2G, PV inverter, and where the Pilentech battery, where the IEEE 2030.5 battery is set up. and the photovoltaic shelter in the EV parking. So these are the facilities that are available in their laboratory for testing the 2030.5, also other ones. Next slide, please. So we conducted 2 tests. One is called software in the loop, and other one is called power hardware in the loop. So the software in the loop, we take an open source software from April. It's a IEEE 2030.5 client, and with this 2030.5 client from April, this can work with self-signed certificate. There is no need of CA certificate, and we were able to communicate from this client to the testing software. And the power hardware in the loop is from the real device. So it's an XFU Pro Schneider inverter in the NLX laboratory. The above pictures that I shown in the other slides. The CA certificate comes from SunSpec for testing. So that does the mutual handshake, and it is hosted in a Linux computer. And once the mutual connection is done, you can see that on the right side picture, the UI tend to be green. Next slide, please. So this is the front end part of the testing software. As you can say that in the testing software, you can configure the device under test with LFID, SFID, and all other parameters that the device has. So this is how you set up the device under test. Then you save the configuration and test it. Next slide, please. So this is the outcome that comes out like test under test and validations. So here you have an expected value, and there is an actual value. Actual value is the value come from the device, and expected value is the one as per the standard from SunSpec. So now I'm going to show a short video of how to use this testing tool. I will take over the presentation. Yeah.
Looks like there's no sound, just so you know, Nathan.
Nathan, we can't hear you and there's no sound.
Yeah, you should explain.
Nathan, can you hear us?
Nathan, we don't hear the audio from the video, so you should comment on that.
And now you're muted.
Well, you're muted.
Sorry. Oh, don't hear the audio. Okay, then I can just explain what it is. This stuff is like this is that I mentioned, like all the configuration about the device that's going to be get tested. First, it has to be stored in the server. So for this reason, we were started to do the feeding the data from the device capability and create the end device. By create the end device means that we create the all features of the device and we save it on the server. Then we move forward to the next ones. Those are registering the end device, which is mandatory. Then after that, we have to do the function set assignment test. So what I'm trying to say here is that we are addressing all the 2030.5 resources. So this is a way how to create the DER curve. And so for this demo, we are not showing any kind of control actions. So we are only trying to show simple DER capabilities and DER settings. This is what I'm saying, that the create DER control comes with a lot of modes. So and you can create the DER controls and curve by selecting the appropriate ones. So all the actions is before the test. Before the test, we have to enter a certain number of actions to continue the test. So this process is, we are creating now the DER capability and DER settings. So this is very necessary for power generation and reactive power test. As you can see that although we create the DER resource, the particular capability is missing, because the capability that has to come from the device once the device is connected to this testing suite. So that action will follow later. So this page is a page that continuously gonna refresh, and once the connection from the testing software to the ad hoc server down on the device, once it got connected, all the test result is going to be shown here. So this is where the our colleague in Italy is trying to launch the ad hoc proxy server that is going to connect to the device. So by this way, our colleague in Italy tried to enable the IEEE 2030.5 from the Schneider gateway. So you can see that from the ad hoc server logs, it's already logging out the values that's going from the device to the testing software. So this is where we get the test values. This is called function set assignment. We have the expected value and the actual value. In the expected and actual value is got compared, and based on the expected value is the one that we can get from the historical data, and the actual value is the value from the device. So this is when I just move a little bit forward. So this is a reactive power. So you can see that we kind of verify what are the parameters that's already included in the for the reactive power test, and this one. This is for power generation. Yeah, so this is how this testing software works. So yeah, that's it from my side. Any questions? I can take it later. Thank you. Back to you, Professor Monti.
Yeah, I was sharing the window. Sorry, it took me a few clicks to share the window back. Now you should see the slide again. Let me know if this works.
Just there you go. Looks good.
Okay, Daniele, the floor is yours.
Yes, perfect. Thank you very much. So yes, we can start directly with the next slide. So good morning, everybody. I'm going to give you now a overview of the architecture and environment where we tested actually the solutions that were just presented by Matthias and Nitin. So we start with the Austrian pilot, where we decided to test these tools in a local energy community. For those who are not familiar with the concept of local energy community, this is an aggregation of various parties like household owners, but also industrial customers or the like, that join this community to gain some benefit out of it. And in particular in Austria, depending on how the resources of the community are managed, they can get some discounts when they have to pay the taxes. So it's quite convenient for them. In this case, you can imagine the challenges associated to the installation of such a monitoring and control tool in each household, not only for operation, but also for debugging purposes. And that's why the colleagues decided to install these or deploy the LPC with a Docker container inside a small computer that is called IoT Max. This can be compared to a single board computer, more or less. And then in order to establish a connection between the IoT Maxes developed, deployed in the various households, they establish a VPN tunnel making use of cellular communication. Despite, let's say, the possible issues that one could have faced in the communication, they were able to both monitor and control in real time the assets in the various households, leading to savings, let's say, not only for the point of view of the community cost, etc., but also installation cost. Next slide, please. We go to the German pilot, where the focus was more on megawatt scale systems. And in particular, here we integrated 2 battery systems, a large PV field, and also a heat pump into an energy management system of the campus. Here, the LPC was still deployed on a Docker container running on a Raspberry Pi. In addition, we tested the effort and time needed for this deployment with respect to the deployment time that we typically needed with our traditional solution. And as I will also mention later, we saw great advantages in implementing, let's say, both monitor and control using the LPC via the Raspberry Pi, in particular making use of the graphical user interface that Matthias showed before. Then we can go with the next slide to the Italian pilot. Exactly. So this was already introduced by Nitin. Here, I would say just will stress again the fact that this was the only pilot where there was not a device that was speaking natively IEEE 23.5, while in all the other pilots we had to make a let's say conversion from legacy protocols, most generally Modbus and MQTT. Then next slide, we can go to the Portuguese pilot. So in this case, the legacy protocol converter was deployed on a dedicated server running Windows. And in this case was mostly used just to monitor the resources. In this case, we had second life batteries and hybrid battery, batteries with hybrid technologies, while the control was still performed using a, let's say, custom developed algorithm developed using LabVIEW. We can go with the next slide to the Spanish laboratory. So as I said, we had 4 pilots plus this laboratory environment, which was actually very useful for us because in this context, the colleagues in Spain were able to stress the performances of the legacy protocol converter in order to provide fast frequency services such as black start, frequency regulation, etc. This was particularly interesting because these colleagues from Spain had a close cooperation with their local transmission system operator. Then we can jump to the next slide. We had various KPIs defined just to measure how, let's say, these demonstration activities ended up in the end. And here there is just a short overview of some of the KPIs, but in general, I can tell you that we have achieved and exceeded all the KPIs. If you want to have more detailed information, you can find everything in the repositories of the project, but just to give you an idea, we were able to test 33 distributed energy resources. In total, we tested this system integrating almost 4 megawatt hours of battery capacity, and we integrated more than 4 megawatt of power among all the pilots. Next slide, please. So as a summary, a few lessons learned. So from the point of view of the LPC, we demonstrated that the deployment via the graphical user interface that was shown by Matthias before, we can, first of all, save a lot of time in the actual deployment. And in particular, as I mentioned, in the German pilot, with the LPC, the deployment time was only 14% of the time that was needed with the traditional solution. Plus, as we saw from the Austrian pilot, there was a huge reduction of the installation cost with respect to what they had before. This solution proved to be lightweight, so that's why it let's say we were able to implement it also on a Raspberry Pi. If you're wondering, the Model 4B with 8 GB of RAM, and we always saw a very limited usage of resources, so with less than 30% of CPU, even though we had a lot of transformation and data exchanged with a time resolution of 1 second. And finally, when it comes to the services for users and system operator, we showed that, first of all, we can integrate seamlessly DRs from various manufacturers with different technologies and also considering different timescales. We were able, thanks to this integration, to reduce peak load consumptions and also increase node capacity without having to change cables or the like. Another final point that I would like to stress, since there was a question popping up before, most of the configuration files that we developed during the project and we use it in our demonstrations are available in our Git repository. So I welcome you to just go in the repo and have a look yourself. And if you have let's say one of those components also yourself, you can already deploy the tool simply changing the IP addresses. So next slide, and I think I'm done. So yes, thank you very much.
Hello, and it's my turn, Nikolai here, and I will then show you some practical examples, particularly the Austrian pilot. Let's please go to the next slide. In Austria, there's a strong push by the country itself, so by the government, for energy communities. There are more than 4,000 across Austria and rising. This number is rising. And I think, so I'm not an expert in the law, but I think Austria is pushing that because they want to get people to work with the energy sector as it is. For many years, it was closed off to big companies and, let's say, thermonuclear industry. So they have pushed these energy communities forward, and to build them up, they allow them to be legal entities. And of course, to incentivize people to join, there's a big or noticeable tax discount for any members participating. Plus, energy price can be defined among the members of the community. So pretty cool. What is also then needed to say is that there are many variations in Austria itself, and there's many variations across Europe and world. So it might not be exactly the case you know, but I will not go into more details today. Next slide, please. The use case we did is in the village Dietach in the Upper Austria. And here I'm showing so how they scaled up. They started in 2022. And from there on, the upper graph is the number of participants in their energy communities. So you can see the government has done a good job getting people to join and incentivize in the market. Next slide, please. And in the village itself, so there's 300 members at the moment. Most of them have a PV system. Some of them have batteries. And as you can expect in a typical village, there's also some restaurants, cinemas, and water pump stations, which are the biggest consumers. But other than these, there is the biggest, say, pressure on PVs and energy systems, energy storage systems in households. And next slide, please. So there are many good things about energy communities in Austria, but the graph I'm showing for the German, I noticed just recently, there are some issues. There are two issues. You can see them on this picture. One, of course, is the elephant in the room. That is the solar production during the day is not used. So the yellow is the production, and the blue is the load, how much the people use the energy. And the second problem, which is a bit more subtle, or very subtle actually, is that this data is shared back to the community from the DSOs only the next day. So they don't really know where they are at the moment. And these two challenges we wanted to target with our solutions in InterSTORE. So if we go to the next slide, you can see, the next one, please, as well. Sorry. Yes, you can see the solution we drafted for them. It's called full chain communication. It was done hastily, so it's not, let's say, optimal. However, it got us to connect to many, so 20 energy resources across Dietach, so across the village, optimally use them so that the users could see the benefit, so that they are in real time monitored and that they see some benefits also on the energy market side. Because I'm coming from Cybergrid. Cybergrid is a VPP solution provider. So what we did was actually, please, next slide. We bundled 20 assets and put them on different markets. So assets on the right, on the left, our solution. We created this full communication chain, which goes via IEEE 2030.5 to each member. And then in our software, we put this to the market, which is ancillary services or wholesale markets. Next slide. So in this sense, we were able to showcase to the users and the community itself that their energy is valuable, that we can make some money with it. And if we go to the next slide, what is even more important is that we can have a system that optimally uses the energy produced. So no big blob in the middle of the day, but rather store it in the batteries and then use it in the later days of the day, particularly in the evening. So we managed to showcase that. I'm very happy that people trusted us. It was, let's say, the biggest step in this work. And if we go to the next slide, I think the biggest lesson learned I want to point out was that, as like I said, we tried to make a use case work, and we didn't have enough time for that. However, the biggest thing I would change if we would do it again is to try to avoid using any hardware. Our solutions are software, they are very good, but to bridge the differences, you need some carrier. And if we could do it, let's say, in a cloud, instead of in a hardware, this would alleviate the cost. And also, as you imagine, it's not very pleasant if somebody is going around your house trying to install a hardware. So this is something I would change. And with that, I hope I could get you some insight into what we did. Thank you.
Awesome. Thank you, InterSTORE team. That was really great. I think this is really exciting and really topical for the SunSpec audience in particular, because this community has been working for a number of years, starting in California, then expanding into other markets and regions like Australia with 23.5 rollout. So it's exciting to see further market expansion with Europe pursuing the standards-based approach for integrating DER systems onto the grid using 23.5. And obviously Europe has more significant challenges, having greater legacy DER penetration, non-standards based systems already set up on the grid. So that's an added layer of challenge that we're appreciative to see your project make strides towards addressing and giving SunSpec members and the broader industry more markets to participate in their products. So very exciting stuff here. I did see a number of questions here in the chat. I think many of them you guys already responded to in the chat. So, but at this stage, I will open it up to see if there's any questions.
I was kicked out from the meeting. I'm back.
No problem. Thank you for rejoining, Professor Monti. So yeah, we're just opening up for the last 2 minutes here to open questions. You can either raise your hand or put them in the chat. Daniel? Yes.
A quick question. If I don't want to give complete access to the network operations center, or I want to limit access only to the negotiated items at the negotiated times, is that possible with 2030.5, or is that really beyond the scope? 2030.5 is really more a communication standard.
I think the easy answer to that is that if you consider 2030.5 over the data space connector, as I presented, was one of the other toolkit we offer, that the prone set of the data space connector is exactly to add the status of sovereignty. So you decide when, for which use case, under which condition, the data access can be performed. So that's what is normally not offered by protocols, but that's the idea of the data space with connection, which together with the data connection, we have a control channel, and the control channel serves exactly the purpose you're mentioning. That's why we combine the two things together.
Excellent. Good work.
Thanks.
Thank you. Tom, you had a question or a comment?
Both. Professor Monti and team, thank you so much for a fantastic presentation. And I just echo Dylan's comments about it's just so gratifying to see you pick up this work in continental Europe. And also, I look forward to seeing you very soon as we'll be coming to your place, I think, in the next couple of weeks. But my question is, now that you've completed this work, what sort of regulatory challenges do you anticipate, or does the team anticipate you'll have across Europe to proliferate this approach?
Well, there is a good moment right now because there is an ongoing activity of the European Commission, which is called Smart Energy Expert Group, within which there is another working group called Data for Energy. And what we are negotiating in that context, and I'm involved, I'm a representative there for the IEEE, so you can see the link, which protocol should be offered in Europe to enable flexibility services. And of course, it's in my interest and my view also that IEEE 2035 should be one of them. And of course, the Commission already said there will be not one N4 solution, but a portfolio, limited, short list. And my point, and I'm expressing that in the committees, is that 2030.5 should be one of them. And I think that would be a very good thing, given that is, as you know better than me, used in other continents, and it makes sense to have a global interoperability because that's what manufacturers are looking for.
Thank you.
Great. So we're a little bit past time, and I do see our audience starting to leave. We have a couple more questions in the chat. Do you guys want to take one more past time, and then we can wrap?
Yeah, don't see the chat right now, but I can.
Maybe I can quickly comment regarding the integration of large DERs. But there's a question regarding experience on integrating these large DERs. I can say that we integrated the largest DR that we integrated was around 2 megawatt. And in that case, the integration included both monitoring and control with a time resolution of 1 second. In our case, we didn't face any problem from the protocol point of view or from the point of view of the communication via the legacy protocol converter over NATs. The only comment that I can make there is that most of the problems might raise from how the control is integrated in the battery, in the, let's say, battery system itself. So if the manufacturer, for some reasons, does not allow you to have a detailed control or a faster control with Modbus, it's very common the case. You may face a problem, but definitely that does not depend on the IEEE 2030.5 or the legacy protocol converter agreements.
Thank you. And so we have one last question. I'll start addressing it, and this will be the last one, then we'll pass out for you guys to have a final closing comments. Matthew asked about contributing to the SunSpec project, presumably referring to the code repository in GitHub. So as far as SunSpec code, that part is not truly an open source project. The code is available on an open royalty-free basis, but we do lock down the code and maintain tight control because these are the foundations of the interoperability standards. And the actual standards development work gets done on a consensus basis within the SunSpec work groups. That said, the InterSTORE project does have more of an open source bent to it. So Dr. Monti, I'll allow you or your team to let people know how they get involved in the InterSTORE project.
I'm happy to close them parallel. I can answer. Multiple protocols are possible thanks to our legacy protocol converter. So any added feature of other protocols you want to add, just go through the LPC. And that means that you can have multiple protocols at the same time. And we did that experimentally in the demo in Rome, as you saw in one of the previous slides. So the coexistence is possible with the system that we built. And that was exactly the main goal of going this way. So my closing remark is, yeah, this is the project. Now there is the community on Cupid. And if you guys are interested in IEEE 2030.5, we'd be very happy to have more people in the community. And this is open. There is nothing to be done to become part in the LF community. You just join the community. You don't have even to be a member of LF Energy to do it. And you can participate to the meetings of the steering committee and contribute or give feedback, everything. The bigger community we build, the more the product can grow and be available for everybody in the real world, as you heard from the colleagues that they're already using it in production. So that's, I think, what CyberGrid did is the best declaration of the value of the work done, because it's real life stuff. Thank you very much for your attention. It was a pleasure to be in this webinar today. Thank you, SunSpec, for having us and to have the chance to present our work.
Yeah, absolutely. Thank you for your contributions and for putting this webinar together with us. Great stuff. And so final reminder, join the SunSpec Alliance, join the work groups, join InterSTORE, and reach out to us anytime. We'll look forward to speaking with you and connecting with you after this webinar. Thank you, everybody.
Bye-bye.
Bye-bye. Thank you.
Thank you. Goodbye.
Bye, everyone. Thank you so much.